Good morning, everybody. So today we're going to get into chapter 11, and we're going to talk about alcohols and ethers. So if we think back to 255 just a little bit, an alcohol is really what? It's an OH, right? And so it's really an organic derivative of what? Of water. So a lot of the things that we know about water can apply to alcohols, right? We know that water likes to hydrogen bond. We know that it has a higher boiling point than you might predict based on its molecular weight, right, because of hydrogen bonding. And we see the same kind of trends for alcohols as well. What is an ether? That's right. So we have an oxygen with two alkyl groups, right? So it shares the oxygen in common with an alcohol, but the physical properties are actually quite different because the functional group is different. Ethers can be polar, but they can't form, or they can't be hydrogen bond donors, but they can accept hydrogen bonds, right? So small ethers might be soluble in water, but larger ethers typically are not, right? So an alcohol would be a what type of solvent if we were using it as a solvent? It's polar protic, right? An alcohol would be a polar protic solvent, but an ether would be a polar aprotic solvent. And so alcohols and ethers are quite frequently used as solvents in organic chemistry. Can anybody tell me the most common ethers that are used as solvents in organic chemistry? Diethyl ether is used quite a bit. You've done extractions with diethyl ether, etc. What else? What was another ether that we talked an awful lot about? 3 letters. It was an abbreviation. Now, NBS, different 3 letters. That was a reagent. Starts with a T? THF, tetrahydrofuran, was a very useful polar aprotic solvent. And we'll be talking about that solvent quite a bit this semester as we get into some other reactions, because it's a very common solvent that's used in organic chemistry. So today we're going to jump in and talk about alcohols and ethers, but I want to have a quick little throwback to chapter 10, just to refresh our memory a little bit from there, get back into the habit of looking at some previous material. So here's some practice problems from chapter 10, which was the free radical chapter. These come out of the ACS study guide. If you don't have one, I'd recommend you get one. Which radical is the most stable? See if we can build a consensus. You think it's D? It is D. You got it right. It is D. Why is D more stable than, let's say, B? They're both tertiary radicals. That's right. So this is tertiary, but it's also what? It has resonance, but what do we call it when we have something on the carbon atom directly bound to an alkene? What's this position? Pardon? It's the allylic position. So this is an allylic radical, and it has resonance that allows it to be more stable than what we would have for B, right? So, good. How about FR5? What is the expected stereochemistry of the organic product from this reaction? So we're starting off with the R enantiomer of this molecule. We're subjecting it to free radical chlorination, and we get this product. What would we expect the stereochemistry of the product to be? What do we think? C is the correct answer. Equal amounts of R and S, meaning that the product is what? It is racemic. Why is it racemic if I'm starting off with the R enantiomer as the starting material? What kind of steps do we have in a free radical reaction? We have initiation, we have propagation, and we have termination, right? And in one of those steps, in the propagation step, right, you have, so let's see, we'll have pH, remember, just stands for benzene. And we will have that radical, right, which then goes on to react with the chlorine to make the product. What do we know about that, the structure of that radical? How do I know there's going to be a radical there? So the initiator, right, will abstract a hydrogen atom from this molecule, and it's going to only abstract this benzylic hydrogen because of resonance. It's the most reactive hydrogen in the molecule. So I know that that's going to be the hydrogen atom that gets plucked off. And that's going to generate that, which then reacts with the chlorine gas to make the product, plus a chlorine radical, which then goes back in and does the chemistry. But what do we know about the structure of this radical? What's the hybridization of that carbon? It is tertiary, but what's the hybridization? It is sp2, meaning what? Trigonal planar. So we have a carbon atom that has a lobe, right, with a radical in it, and we have, let me draw it like this a little bit. So we have that, draw that coming out towards us, and going back behind us would be the methyl group, and so it is trigonal planar, right? And so this electron is actually in both sides of the orbital, right? I just drew it on the top. But the chlorine gas can come in and react at either the top, which would give one enantiomer, or the bottom, which would give the other enantiomer. And what's the probability? It's 50-50, right? It's just as likely to attack from the top as it is from the bottom because there's a plane of symmetry through this molecule. The top cannot be distinguished from the bottom. And that's why we end up with an equal amount of the R and the S isomer in this particular reaction. So this is the kind of reaction that if you were to do would get you fired at your job, because you're starting off with something that's enantiomerically pure and probably pretty expensive, and you're making something that is dirt cheap, and that is never a good business model, right? Bringing in expensive things and selling them for cheap is not going to make any profit, so not a good way to do business. How about FR6? What is the expected product of this reaction? What do we remember about the differences between free radical bromination and free radical chlorination? Well, the bromonium ion gets formed when we have an alkene in bromine, right? So a little different here. This is a free radical reaction. Remember, bromine, free radical brominations are more selective. They had a higher energy of activation, right? And so they tended to react with the most reactive hydrogen only. And what would that be? D. Remember, the reaction of a tertiary hydrogen is greater than the reaction of a secondary hydrogen because of radical stability. Remember, a tertiary radical is more stable than a secondary radical, is more stable than a primary radical, right? Just like with a carbocation. And so the product that we would expect to get out of this then as the major product is D. And free radical bromination is actually very, very good, and you can actually do this in a lab, get this at about 100% yield, more or less, and it's a good reaction. If we had done free radical chlorination, we would have gotten a whole slew of different products, because the chlorine radical is so reactive it'll react with just about any hydrogen that it comes into contact with in an organic molecule. Which is the reactive intermediate when 1-octene is treated with HBr in the presence of peroxides? There should be two up there that we can eliminate pretty easily. What would they be? If you were taking your exam, your ACS exams, which two would you eliminate here?
B and D.
You'd eliminate B and D? Why would you eliminate B and D? Hold on. Okay. You would eliminate A and C? Why would you eliminate A and C? Okay, no bromine in either one of them. Mm-hmm. Remember, we're reacting with HBr. The correct answer here is B. So when we react HBr with 1-octene, in the absence of peroxide, what kind of addition do we have? We're going to add HBr across the carbon-carbon double bond in what kind of fashion? Rethink it. How are we going to do it? We're going to add HBr across the double bond in a Markovnikov or an anti-Markovnikov fashion. Markovnikov fashion, right? Meaning the hydrogen goes to the carbon with the most hydrogens, the bromine goes to the carbon with the least number of hydrogens, right? Because we go through a carbocation intermediate. Here we don't go through a carbocation intermediate, and the bromine radical adds to the alkene first and generates a radical intermediate. And we know that it can either attack the number 1 carbon or the number 2 carbon. If it attacks the number 1 carbon, you end up with B as the intermediate. If it attacks the number 2 carbon, you end up with D as the intermediate. Why does it prefer to attack the primary or the number 1 carbon and give this radical as opposed to this one? That's right. It is the most stable radical. And so we can actually add HBr across the carbon-carbon double bond in an anti-Markovnikov fashion if we have something like peroxides around, because peroxides initiate free radical reactions. Okay? All right. So let's get into the new stuff. We're going to start talking a little bit more about alcohols. We've already talked an awful lot about alcohols, right? We've talked about a variety of things that we can do with alcohols already from 255, but we're going to continue on and spend an entire chapter talking about alcohols and ethers. They're a very important functional group. Alcohols, of course, have the hydroxyl group, as Ahmed just mentioned, right? And so if we have an OH group attached to a saturated carbon atom, we typically call those alcohols. But we can have other types of quote-unquote alcohols. We can have enols, where the OH is attached to a alkene. We talked a little bit about those last semester. They are not particularly stable, and they tend to undergo tautomerization. Does everybody remember that word? What does it mean to tautomerize? Okay, something rearranges in a way, and so this could tautomerize to a ketone. So remember, ketones and aldehydes can tautomerize to enols. And then we can have phenols, where we have an aromatic ring like benzene. Actually, phenol is benzene attached to an OH group. These all have properties similar to alcohols, but they have different chemistries. They have different pKa values, for example. What might you expect the pKa range to be for a typical alcohol, like ethanol or methanol or something like that? 16 to 20 is a good range. Yeah, somewhere around water, right? Water has a pKa of about 16, a little less than 16 actually. So we would expect alcohols to be about that. So a primary alcohol is going to be somewhere around 16-ish. You know, some other alcohols might be a little higher than that, might be a little lower than that, depending on what's attached. But a typical alcohol, that's the range. Where might we expect a phenol to be? So if I was to draw a phenol, would we expect it to be in the same range? Let me draw it up here so everybody can see it a little better. Would we expect the phenol to have the same pKa value as an alcohol? We wouldn't. And why wouldn't we? When I protonate it? So when I deprotonate it, okay, so when I remove the proton and I look at the anion, right, that's how we always determine whether or not something's a stronger acid than something else. And let's just compare that to ethoxide. The phenol, or the phenoxide anion that we get, this negative charge can actually be resonance delocated throughout the ring, right? I can draw multiple resonance structures for that. And as a result, the pKa should increase or decrease? Decrease. The acidity increases, but that means that the pKa actually decreases. So if we know that an alcohol is going to be somewhere around 16, and I can't draw resonance structures for it, what might you predict the phenol, the pK of the phenol? 10. 10's a good number. 10 to 11 is a good number for a phenol. Now I can add substituents on there and I can change it, but just good old-fashioned phenol is somewhere around 10. 10 versus 16, is that a small difference or a large difference? It's a large difference. At 6 orders of magnitude, that's 1,000,000, right? So phenol is substantially more acidic than ethanol because we can draw these additional resonance structures. So let's look at some examples of the classics here. Ethanol, right? Also known as ethyl alcohol. What's another name for ethyl alcohol? Common name other than beer or wine. This is also known as grain alcohol, right? You'll hear the old timers talk about grain alcohol, right? This is what the moonshiners make out in the woods, right? How would we name this one? Isopropanol is a perfectly acceptable name because we have an isopropyl group attached to an OH. We can also name it 2-propanol. You all know this is rubbing alcohol, right? You all know this is rubbing alcohol. You can go to Walmart or Walgreens or wherever you go and you can buy this as a 70% solution or a 91% solution, and you use it to treat cuts and scrapes and this, that, and the other, right? How would we name this one? Would we call this one pentanol? Cyclopentanol, right? Because we have a cyclopentyl group. Okay? So cyclopentanol would be the appropriate way to name this. Why don't I have a number there? Yeah, no matter where I put it, it's going to be 1 cyclopentanol, so we can ignore the number. Now, if we go by what Bailey had said and called it pentanol, numbers become important, right? Because we can have 1 pentanol, 2 pentanol, 3 pentanol, and so the numbering would be very important there, okay? And then, of course, we can have enols and phenols that are, you'll notice that the OH is always attached to an sp2 hybridized carbon, okay? Ethers, Anna mentioned that that's ROR, right? Here it says ROR prime. The R's can either be the same or they can be different. Okay, but they can be alkyl, they can be alkenal, they can be alkynyl, or they can be aryl. Aryl meaning aromatic, right? So just any carbon group attached, as long as it's not part of a carbonyl, right, we're in a situation where we can have ethers. Okay, so some common examples: dimethyl ether. We have this ether where we have the alkene attached to the oxygen. This is known as ethyl vinyl ether. And here we have a situation where we have a methyl group and an aromatic ring, okay? This type of an ether where the 2 R groups are identical, we call that a symmetrical ether. Why is it symmetrical? What symmetry element allows me to say it's symmetrical? What kind of symmetry does it have? It's got a mirror plane. Where? Right through the oxygen, right? We've got a mirror plane. So the left-hand side has to be equal to the right-hand side. So we just call them symmetrical ethers. These are unsymmetrical ethers, okay? And pretty obvious. There's no mirror plane of symmetry that relates the left side and the right side of this particular molecule, okay? Melting points and boiling points of alcohols and ethers, okay? as we increase the size of the R group for what we're going to call straight chain alcohols, you can expect their melting and boiling points to increase. The more carbon we add, the higher the boiling point, basically. Okay? And so solubility in water, right? Small alcohols are going to be completely soluble in water. Larger alcohols are going to be insoluble in water. Our good friend ethanol, we know for a fact from our everyday experience, is perfectly soluble in water. I have yet to go to the bar and order a mixed drink and it come out in 2 layers, right? It's all mixed together. Small alcohols like methanol, ethanol, propanol, butanol, those are going to be completely soluble in water. When you're starting to talk about 5 or 6 carbons up to about 8, you're going to have limited solubility, and above 8, we typically say they're not soluble. Okay? So number of carbon atoms that you have is going to be very, very important. So if we look at some examples, these are all completely soluble in water. You can take methanol and an equal volume of water, mix them together, and it just forms a homogeneous solution. However, when you get above 3, you start to get into some solubility issues. So here we've got 1 butanol. We can only get about 8.3 grams of butanol into 100 to make 100 milliliters of solution with water. And let's see, how many carbons do we have here? 1, 2, 3, 4, 5, 6, 7, 8. So here we have 9 carbons. So how would we name that? What would the parent be? No name, right? And what do we need to do to name this? We need to remove the A and E ending and add OL, right? So this would be 1 nonanol, right? And notice you're only going to get about 0.05 grams per 100 milliliters in there. It's going to form 2 layers. You're going to have a bilayer situation because there's all this fat, right? This organic stuff. So you need to remember your solubility rule of thumb that we talked about last time. And what was that? That was the 5 carbon rule. Very good. And what did it say? Okay, so for every functional group that can what? They can form hydrogen bonds. If we have 5 or fewer carbons, we're typically assume it's going to be soluble in water, right? Now it's just a rule of thumb. There are things that clearly will violate that, but that's a good rule of thumb. So I know that this more or less kind of seems to follow that rule of thumb, okay? Now we know that alcohols and ethers all have dipole-dipole interactions, right? They have polar bonds. Carbon and oxygen have different electronegativities. So we are going to have dipoles, and they are going to be permanent dipoles, okay? But alcohols are also capable of forming hydrogen bonds, right? And so if you think about methanol, a simple example here, we have an oxygen atom that has lone pairs, obviously, and a hydrogen atom attached to that. And so 2 of these molecules can actually come together and form a hydrogen bond, where one of the alcohols, the hydrogen on the OH, is actually forming a hydrogen bond with the oxygen of another molecule. And this actually can form a very extensive network. It's not just 2 molecules, because you can imagine this hydrogen now hydrogen bonding with another molecule, so on and so forth. And so what you would predict, right, is you would predict, based on that hydrogen bonding, that the molecule is going to have a higher boiling point. Why is it that hydrogen bonding leads to higher boiling points? Okay, they are strong. That's right. But why does that lead to a higher boiling point? That's right, because we always have to put energy in to break a bond, right? The thing that I told you last semester about things that you might have learned in your biology class or biochemistry class when you get to it that is wrong is that breaking a bond leads to energy release. That's not true, right? All bond-breaking events are endothermic or exothermic. They are endothermic. And so to boil something, I got to put energy into it to convert it from the liquid state to the gas state. And in doing that, we're going to break those hydrogen bonds, right? So it's going to take more energy to break hydrogen bonds than it is to break dipole-dipole bonds. And so we would expect ethers to have lower boiling points than alcohols because of this. Okay? The size of your R group matters, not just in terms of how many carbons you have, but whether or not the alcohol is primary, secondary, or tertiary. And what you'll find is that primary alcohols typically have higher boiling points than tertiary alcohols because primary alcohols are more able to form a hydrogen bond. Why is that? Why can a primary alcohol form a hydrogen bond easier than a tertiary alcohol? There's less stuff around it, right? There's less steric bulk. So if you were to actually draw this and explain this to me, how would you do that? If I asked you on the exam, explain to me why a tertiary alcohol would have a lower boiling point than a primary alcohol of similar molecular weight. How would you draw that? A lot of crap around it. That's right. So basically what you do is you may take two primary alcohols, show the hydrogen bond, and show that the big groups can be kind of far apart from one another, right? But then if I take two tertiary alcohols and I try to bring them close together to form a hydrogen bond, you would see that the big stuff kind of gets in the way of each other. And so the hydrogen bond would be weaker because it can't get as close, right? And so that's how we would describe that graphically. So when we look at some examples here, right, so we have an alkane, an ether, and an alcohol, all of about the same molecular weight. You notice that butane has a boiling point of about 0 degrees Celsius, right? So you have a butane bottle at home that you may use to, if you use butane, most people use propane these days, but you could use butane in your charcoal grill, right? Well, if it gets down to 0 degrees Celsius, butane doesn't work very well because it actually liquefies. It doesn't go into the gas state very well. That's why most people use propane these days. It's a little more, you can go down lower. But if you go to this ether, which is about the same molecular weight as this alkane, you notice that the boiling point here is 11 degrees. That's pretty substantial. And if you go from this ether to this alcohol, you can see a huge jump in boiling point. This is near the boiling point of water, right? 97 degrees Celsius. So just adding this ability to form hydrogen bonds has a dramatic ability to increase the boiling point. If you look at primary, secondary, and tertiary alcohols, you'll see that that follows based on their ability to form hydrogen bonds. So tert-butanol has a boiling point of about 83 degrees. How would we name this one? Why would we name it 3-butanol? 2-butanol, right? We always want to give the OH the lowest number, right? So we wouldn't number 1, 2, 3. We would number 1, 2. So this is 2-butanol, and it has a boiling point of 98 degrees. And this would be 1-butanol. We have to give the number here, right? Because we can have 1 or 2-butanol, and that would be 118 degrees. So again, everything's going to follow the 5-carbon rule. Alcohols and ethers with less than or equal to 5 carbons per OH group are going to be water soluble, and alcohols that have greater than 5 carbons are typically going to be insoluble, and we're typically going to be able to get alcohols and ethers into organic solvents. And so those organic solvents are things like dichloromethane, diethyl ether, THF. We'll be able to dissolve those molecules in there fairly easily. Okay? So if we think of some interesting alcohols that we're probably all fairly familiar with, one of my favorites is ethanol, right? We get this from the fermentation of a variety of carbohydrate-containing things, right? So if we ferment things like grapes, we make wine. When we ferment things like corn, we make grain alcohol or whiskey. But nonetheless, the main alcoholic component in all of those things is ethanol, right? And so this is probably one of the most readily recognized alcohols of everything that we'll talk about. What else is ethanol used for these days? It's used in gasoline. Anybody know why? Other than the political reasons? They used to use a thing called MTBE, methyl tert-butyl ether, as an oxygenating agent in your gasoline. You have to have an oxygenating agent in your gasoline so that you don't put out a lot of carbon monoxide, which is poisonous, out the end of your tailpipe. MTBE was an excellent oxygenating species. But most gas tanks, when you go to the gas station, are buried underground. And they have a habit from time to time of leaking a little bit. And MTBE was finding its way into water sources. And MTBE is a potential carcinogen. Kind of bad to be putting cancer-causing things down into people's drinking water. Ethanol, however, if it leaks out and makes its way down to the reservoir, you just got really dilute beer, right? And it's not carcinogenic. And so there are real reasons why they made the switch to ethanol. It's not just because the farmers have a good lobby and we're able to lobby to get ethanol to replace MTBE in gasoline. You have to have some type of oxygenating species to meet EPA emissions requirements, okay? So that we can breathe clean air, or cleaner air. I shouldn't say it's absolutely clean. So here's an example of methanol. This is also known as wood alcohol. You will probably know that you don't want to drink wood alcohol, right? Because it causes what? It causes us to go blind. Anybody watch moonshiners on the Discovery Channel? When they're distilling, they take about the first quart or two and they throw it away. They call it the heads. Anybody know what's in that? Methanol. There's a lot of methanol that is distilled out at the very beginning of a distillation process to make grain alcohol. Because grain alcohol is mostly ethanol, but the yeast will also make some methanol in small quantities. So you never want to drink that first quart or two that comes out of the still because it contains poisons. So if you're buying illegal liquor, I hope that your provider knows how to do distillation properly and knows a little bit of chemistry, because this can kill you, okay? And as little as 15 milliliters of methanol can cause blindness, and 100 milliliters can cause death, okay? And we'll talk a little bit about how these things get oxidized into other products in the liver later and how they actually cause the blindness. 2-propanol, also known as rubbing alcohol, right? It's a very good antibacterial, general antibacterial, so you can use it to clean a variety of things in your house to kill bacteria. Sometimes they'll use a little bit of that to help sterilize medical instruments, etc. But a lot of people, especially athletes, will use it just to rub on their skin to give a cooling effect, right? Because it evaporates quite quickly and it cools, gives you that cooling sensation. So it's good for that. And then ethylene glycol, which is a diol, if you will, right? It's 1,2 dihydroxyethane is one way to name it, but most people call it ethylene glycol. This is what used to be an antifreeze. It is no longer used in antifreeze for most purposes. So this would have been the old like Prestone that was kind of a yellowish green color, fluorescent green color. They gave it a kind of a yucky looking color because it's very, very toxic. And people used to go out and change their antifreeze. You had to change your antifreeze every 40 or 50,000 miles used to. And they would change it, leave it in a bucket out in the yard, the shade tree mechanics, and dogs would come up and start licking it, and they would continue to drink it because it's extraordinarily sweet. It's sweeter than sugar. I've actually taken a little bit and touched it to my tongue before. I don't recommend that you do that, okay? But it is extraordinarily sweet. And so I can understand why somebody or something would taste that and go, yum, and keep going. So it's very, very toxic, and so we don't use it anymore in modern automobiles. We use propylene glycol, which has an extra carbon, and it's not quite as toxic. And so actually propylene glycol you will find in some foodstuffs. So, but it still has the ability to function like an antifreeze. There are some interesting ethers that you ought to know about. These are called the crown ethers. Can anybody tell me why they call them crowns? It kind of looks like a crown. It's kind of hard to tell if you look at it in two dimensions, but if you were to build a model of this, each one of these carbon atoms is what shape? What's their hybridization? They're sp3, so what's the shape of each carbon atom? It's tetrahedral. What's the shape of each oxygen atom if you count the lone pairs of electrons? They are also tetrahedral. And so when you put all these tetrahedra together and make a ring out of it, they form a crown with the oxygens all pointing in one direction. It kind of looks like a royal crown in a way. But they have these things that, these cavities that things can fit in. And so these so-called crown ethers can actually coordinate and make complexes with cations, things like potassium or things like lithium. And you can actually use these molecules to separate cations from mixtures. So when you mine things like salts, it will typically be a mixture of lithium chloride and potassium chloride and sodium chloride. And one of the ways you can get some of these other things out is by treating them with these crown ethers and actually complex things that will fit inside and pull them out by extraction with some type of organic solvent. This is called host-gas chemistry, and if you're more interested in that, Dr. Wallace, this is the kind of chemistry he does. He does this host-gas molecular recognition kind of stuff, and he uses crown ethers a fair amount. So he's an expert in this area, and so you can use this kind of stuff for some interesting chemistry. And it turns out that things similar to this are actually in your body right now, in your membranes. You have ion channels that allow certain ions to go through a membrane and get inside or outside the cell. They're not crown ethers, but it's the same kind of situation. You make a coil that kind of a cavity, and only certain things of a certain size can get through, and they form these ion dipole interactions and allow for the bonding to occur. Here we have parapolone B, which is a cockroach sex pheromone. It has an interesting ether here in that it's a three-membered ring, and we call those epoxides. Would we expect the chemistry of the epoxide to be similar or different than the chemistry of a typical ether? We would expect it to be quite different, and why? I will tell you that epoxides are more reactive than a typical ether. Why? Ring strain, right? Because we have a strained ring, it will react with nucleophiles where a typical ether will not. And we'll talk more about those chemistries in later chapters, okay? This was actually this was isolated, and chemists actually worked on finding ways to synthesize this because there are chiral centers. It actually proved to be a challenge. Here's a chiral center, here's a chiral center, here's a chiral center, and here's a chiral center. So 1, 2, 3, 4. 4 chiral centers, 2 to the 4th possible stereoisomers, not counting the fact that you have cis and trans for that alkene. So if you add that in, you have even more. So this was actually a challenge to make, and organic chemists spent a lot of time trying to make a cockroach sex pheromone. What would be the practical purpose of making a cockroach sex pheromone?
Bug trap.
Pardon?
Bug trap.
A bug trap, exactly. You build these cockroach motels. Why do the cockroaches go in there? Because they think there's some fun going on. And that's exactly what they think. And so they lace it with this cockroach sex pheromone, and it attracts the cockroaches in there. But when they get in there, there's sticky substance that they just can't get back out, and they sit in there and they starve to death, right? But they're tricking them, right? They're getting them all excited, and they walk in, right? Maybe a little more important, epithalone B. This is an anti-cancer drug. This is actually a very complicated organic molecule, and in fact, you can see a variety of different functional groups. Here's the epoxide, that three-membered ether ring that we need, right? If it's not there, this doesn't work. But also you have alcohols, right? So it's also important here that we have these alcohols, and we have ketones, and we have esters, and we have alkenes, and we have this ring. And so Very complicated little molecule, contains a lot of different functional groups. But you got to have that epoxide ring for this to work. So it is a very potent anti-cancer drug. And I believe this one is used in the treatment of breast cancer, but I'm not 100% sure on that anymore. All right, so we know that some physical properties of these things. We've seen some interesting examples on why studying these are kind of important. Let's talk a little bit about ways in which we can make alcohols, ethers, and epoxides. Okay. Now, we mentioned that alcohols are organic derivatives of water, and we studied last semester in chapter 7 or 8, addition reactions. So we know we can take an alkene, right, and we can add water across the carbon-carbon double bond and make an alcohol. And we can do that in either a Markovnikov or an anti-Markovnikov fashion. But we can also make alcohols by treatment of alkyl halides with hydroxide, right? And this is going to be an SN2 process. Why is this an SN2 process, this first one that's shown? How would you know that this has to be an SN2 process? Pardon? All right, we have a primary alkyl halide. Very good. Good leaving group. And a strong nucleophile. All of those things point to an SN2 reaction. So we can convert alkyl halides by treatment with hydroxide, especially if they're primary, into primary alcohols through an SN2 process. We can also take alkoxides and we can make ethers through a same type of reaction. It's SN2, right? We can take methoxide plus one chloropropane, and we can get an unsymmetrical ether through an SN2 reaction. We can also take ethyl bromide and ethoxide, notice the same number of carbons on both the electrophile and the nucleophile, do an SN2 reaction and make what's known as a symmetrical ether. When we make ethers by reaction of some type of alkoxide with an alkyl halide, this is known as the Williamson ether synthesis. And it is a reaction you need to commit to memory. Organic chemists speak in terms of named reactions. And we're going to learn a lot of named reactions this semester. And the Williamson ether synthesis is our first. So if I come into class and I start talking about the Williamson ether synthesis and I don't draw anything on the board, you need to know that that is the reaction of an alkoxide with an alkyl halide. It is typically between a primary alkyl halide and a primary alkoxide. Okay? But that is what is the Williamson ether synthesis. Okay? Now, we talked about last semester about taking alkenes, reacting them with water, and forming alcohols through this type of mechanism. Whoop, there we go. Right? This is a multi-step reaction. We need to have water and an acid catalyst. What's typically the acid catalyst that we use? Sulfuric acid is my favorite, but what else will work? I think we talked about two acids. Sulfuric acid was certainly one. It's the one that I like. What's the other one? Acetic acid is too weak. We need a stronger acid. It's an organic acid that's kind of like sulfuric acid. Anybody remember what it was? You're close. Say it. Para-toluene sulfonic acid. Okay? But it is a sulfonic acid. Those are common acids that are used in this reaction. Okay? Now, since we are generating a carbocation, what do we have to pay attention to? What do you think? Amid, what do we have to pay attention to if we generate a carbocation? We've got to focus on the stability, which leads to what? Possible rearrangements. Not the case here, because it can't rearrange to anything more stable than the tertiary, right? Notice we're pushing 2 electrons at a time. We start with the alkene. We protonate from the acid. We generate a carbocation. That carbocation that gets attacked by the water, it's a nucleophile here because of the lone pairs of electrons. We end up with a protonated alcohol, which then gets deprotonated by water or the counterion of the acid. It doesn't really matter which. And you end up with the alcohol plus your acid catalyst back. This is acid catalyzed. We don't need a lot of acid. Notice each step is reversible. So how do I drive the reaction from alkene to alcohol? Whose principle do I use? I'm going to use Le Chatelier's principle. And what am I going to do to ensure that Le Chatelier's principle pushes this reaction to the right? I'm going to use a lot of water. Why am I not going to use a lot of alkene? Le Chatelier's principle also dictates if I used a lot of alkene, it would push it to the right as well. Why would I choose to use a lot of water over a lot of alkene? Water's cheap. Yep. I can just get a glass of water real easy just about anywhere, pour it in, and get this to work, right? Now, if I want it to go in the reverse direction, what do I need to do? I need to remove the water, right? And so going from an alcohol to an alkene is known as we talked about it last semester, and an elimination of water is a dehydration, right? And so we use the excess acid, dehydrating acid, and we remove the water, right? So this is just the reverse of that dehydration that we talked about. Okay. Let's go ahead and pick up here on Friday. So I need your inverted lecture turned in today. So on your way out, just leave it up here at the top. Make sure you have both your name and your partner's name on your inverted lecture. I've got about 20 of you signed up for Remind. There's 8 more of you that need to get signed up. Please get signed up for Remind. And I think there's 3 or 4 more of you that still need to get signed up for Sapling. And Chapter 11 homework is currently up and available on Sapling, so please get signed up for that.